Hello everyone, today we're going to talk about another type of differentiation called implicit differentiation. Throughout most of your high school careers, you've been dealing with equations like the top one on the left, the y equals 3x squared minus 5x plus 6 problem. That's called an explicit equation, and that's one where we have already solved for y, we've gotten y by itself. On the other hand, an implicit equation is one where the y's are sprinkled throughout the equation, and that's the bottom one, the x squared plus 9xy plus y squared. This you may recognize from Algebra 2 as the basics of a circle, a hyperbola, an ellipse. All of these are ones that are more implicit, and you have to have a different type of derivative for that. Now the good news is all the same rules for taking derivatives apply, but we just have one extra step. We're going to have to solve for dy dx at the end in order to finish the problem. So we're going to start by looking at an explicit equation and then ease our way in. So starting with y equals 3x squared minus 5x plus 7. It's a very easy derivative. The derivative would be 6x minus 5. Now notice when I take the derivative of the y, I get dy dx. Remember, the derivative of y is dy dx. If we rearrange the equation, we can see it still makes sense. So all I did on the bottom is I just flipped it up a little bit, and then I took the derivative of the new equation down at the bottom separately. So the derivative of 5x is 5, the derivative of 7 is 0, the derivative of 3x squared is 6x, and the derivative of y is dy dx. So my final step, and this is the new step for implicit differentiation, is to solve for dy dx. So you get the dy dx by itself, and you see that you get the same answer. So let's bump it up a little. So we have another equation, 3y equals x squared minus 4x plus 2. So since I have a times 3 in front of the dy, it makes sense that there's a times 3 in front of the dy dx. So the derivative of 3y is 3 dy dx. And then the derivative of x squared is 2x, and the derivative of 4x is 4, and the derivative of 2 is 0. So my final step, I need to get the dy dx by itself, so I'm going to divide by 3, and there's the dy dx by itself. If I scramble it, it should still work, just like the last slide. So here's the exact same equation, scrambled up. So I take the derivative of that, and once again, the derivative of 4x is 4, the derivative of 3y is 3 dy dx, the derivative of x squared is 2x, and the derivative of 2 is 0. My next and final step is to solve for dy dx. So bring the 4 over, divide by 3, and you see you get the exact same answer. All the rules that apply to x also apply to y. We just have to tack a dy dx onto the end. So we have x squared plus y squared equals 25. We're going to use the power rule. The derivative of x squared is 2x. The derivative of y squared is 2y. But since it's the derivative of a y, we have to tack on a dy dx. The derivative of 25 is 0. Our final step is to solve for dy dx. So I'm going to move the 2x over and then divide by 2y. So move the 2x over, divide by 2y, simplify if possible so the 2's cancel out, and I get negative x over y for my derivative. Remember our product rules. This trips people up every time. If we have a derivative, we want to find the derivative of xy equals 10. X times y, that's a product rule, so I have to use the product rule. So underneath here, the product rule is take the first, the x, leave it alone, take the y, the derivative of y is dy dx, plus the second, which is y, leave that alone, times the derivative of x, which is 1, and then the derivative of 10 is 0. Once you get to that next equation, you've got to get the dy dx by itself, so we're going to bring the y over and then divide by x, and then we're going to get our answer. Now you might notice that I wrote a dx dx there. You don't need to. Dx dx is 1. The reason I wrote that is to show you that we're taking the derivative. For that equation, we take the x times the derivative of y plus the y times the derivative of x. The derivative of x in this case is just 1. Right? So we don't write the dx dx's because that just would take too much time. Now, students sometimes have difficulty when there's a coefficient involved in a product rule because this effectively makes 3 different factors. So you have a couple of options. One option, here's an example, we have 3xy equals 7. Anchor the 3 to the x value. So then when I use the product rule, the 3x left alone times the derivative of dy dx plus the y left alone times the derivative of 3x is 3, and you get your answer. Another option is to factor it out front. Move the 3 out front, and then just take the derivative of xy using the product rule. Either way is fine. I personally tend to use the anchored method, but either one will work fine for you. So, process for solving for dy dx, it's parallel to the process for solving linear equations. It just looks a little harder. First, we use the distributive property to get rid of parentheses. We use addition and subtraction to move all the dy dx terms to one side and the rest of the stuff to the other. Factor out the dy dx, and while it may be a huge coefficient, that's all it is. It's just a coefficient. And then divide by dy dx. So I'm going to give you an example now. If you need to, press pause and you can come back when you're finished writing all this down. Alright, so here is a nice equation. You can see the y's are sprinkled throughout the problem, and we're going to take the derivative of that. So to do that, we're not going to write dx dx. You don't have to. I'm going to put the dx dx's in there just so you can see it's consistent behavior. So 3x squared. The derivative of 3x squared is 6x dx dx minus, now here I'm using the bringing the 5 out front method. So I factor the 5 out front, and I took the derivative of xy. I use the product rule. So it's x times the derivative of y, that's the dy dx, plus y times the derivative of x, that's the dx dx, plus the derivative of 7y squared is 14y, dy dx. The derivative of 8x is 8, dx dx. The derivative of 2y is 2, dy dx, and the derivative of 7 is 0. Now all those dx dx's, they're just ones, so I just got rid of them basically in that second step. From here on out, it's just an algebra problem. We need to get all the dy dx's on the same side, and we need to get everything else to the other. So I'm going to spread it out. I'm going to distribute that 5 across. So if I distribute that negative 5 across, I get that. I'm going to move the dy dx's to one side and the rest of the stuff to the other side. So here's all the dy dx's on one side, all the other stuff on the other side. Then I'm going to factor out a dy dx. So here's the dy dx all factored out. And then to get dy dx by itself, I just divide. And that then is my answer. That is the derivative. I know it looks like a mess, but it's actually not too bad. I think I'm going to do one more example, and then I think that's it for today. So this can't be solved for y because of the sign y. So therefore we have to use implicit differentiation. So we take the derivative of 2y, we take the derivative of x squared, and we take the derivative of sine y. Well, the derivative of 2y is 2 dy dx. The derivative of x squared is 2x. The derivative of sine y is cosine y dy dx. Now I'm going to move the dy dx's to the same side, leave the 2x on the right hand side, factor out a dy dx, and then divide to get my final answer. And there it is. That is implicit differentiation. What you have to do is differentiate both sides with respect to x, and then solve for dy dx. Okay, I'll see you in class tomorrow.